All right, good morning, everybody. It's good to see all of you. I hope that your week is going well and happy to be back with you. Couple of quick announcements before we jump into the new stuff for today. First of all, there's always a homework assignment on the horizon. And so there is one due tomorrow night. So this is actually the second part of homework 10. I remember I split up this homework into two parts. You turned in some of it already on Tuesday, but there's another part of this which will be due tomorrow night. I am planning to spend some time today just working through some of those problems. I actually think there's quite a number of problems listed there. So I'm going to go through some of them just with you in class, even if you haven't looked at them yet. And all you'll have to do is kind of write them down and be ready to transfer them to your assignment. So I'll definitely help you out with that. In the next 2 hours, we'll do that. Also, just a heads up, our next midterm is actually 2 weeks from today. And so I'm already starting to think about that. I am going to give you some extra credit opportunities again, just like I did with the first exam. And the first of those is actually going to be this weekend. I'm going to ask you to watch a video and take notes on it as usual and submit those notes. And just to make it a little bit more fun, it's a video that I recorded a few years ago, and there's a little mistake in the video. So I'm going to have you find the mistake for even another extra point. So that'll really get you making sure you're paying close attention when you're watching the video. I'll send you the link to that and the place to submit that on Canvas a little bit later today. But there'll be a video for you to watch over the weekend. It'll be nothing to do with anything we've been doing in class so far. It'll basically be a preview into the next chapter. So I think that'll work well. And I'll ask you to watch that before our next class. This weekend, we have our daylight savings time shift as well. So that means I actually like it because it's not going to get dark so early. But unfortunately, we lose an hour of sleep on whatever night that is. So just pace yourself a little bit this weekend with whatever work you have to do. And at least for my class, it'll mostly be watching that video. I don't know if you've noticed, I'm kind of adopting this now in the education world, they call it the flipped model of teaching. What that is where I have students, much more than I did in the past, I have students watch videos outside of class, and that gives us time during class to do problems and like work on the homework and do group work and stuff like that. So I have been adopting that a little bit. As you'll see today, I'm going to do some of the homework with you in class. And next Tuesday, same thing. If you guys hold up your end of the bargain and watch this video over the weekend, then next week on Tuesday, I don't have to rehash all of that again. Instead, I can actually do problems that are based on that video. So I think that hopefully will work out to be an effective way for you guys to learn as much as possible. But yeah, the midterm is 2 weeks from today. It's a little early to start studying for it in the sense that we still have quite a bit of material to cover next week even. So if you were to go look in the resources folder, it is there. You can look at it, but you'll see a lot of questions. You're like, oh, I don't know about what this is about. Or, I don't know what that is about. So I would say for this weekend, focus on the video and just the homework that's going to be coming for next week. Does that sound like a plan? Everybody with me on all that? Okay, great. And of course I have office hours. I have office hours today after my last class gets over, which is at 5:30. And then tomorrow in the evening, I'm going to be around like I always am on Friday evening. Since the homework is due tomorrow night, I will definitely be around. And you can come in Zoom or in person. Either way is fine with me. There's been a lot of quiet office hours for me this semester compared to normal for Math 350B. It suggests to me that either people are totally nailing everything or people are not putting in the work they need to really learn the material. So if it's the latter, there is still plenty of time left in the semester to kind of right the ship on that, okay? Because I want everybody to do well, and I'll do as much as I can to help with that. So stop by my office hours if that could be of help for you. Okay, great. No questions so far, just on the overview. If not, I am going to recap, as I always do, where we left off last Tuesday, just 2 days ago. We're still in the middle of chapter 4. We're kind of in section 4.6 right now, which is about the concept of a basis for a vector space. This is probably the central focal point of vector space theory, the idea of a basis. So what is a basis, guys? For a vector space. If I have a vector space V, a basis is just a set of vectors listed out. These could be polynomials, these could be matrices, these could be functions, just whatever the universe is, right, that you're working in. You have this set of vectors in this vector space, and they are a basis for V if two things are true, guys. Two things are true. First, S has to span V, right? And secondly, S has to be Li. Li, remember we talked about that quite a bit on Tuesday. That just means they are cheap. They are efficient as a spanning set. So if S is both a spanning set and a cheap set, i.e. linearly independent, then it's a basis, okay? And as we saw on Tuesday, it turns out that the process of checking these two properties is almost the same. For both properties, it's almost the same thing you're going to be doing. Namely, right, you lay your vectors into the columns of a matrix. And if I want to check whether they are a spanning set, I'm going to augment that matrix with these, I kind of did this number symbol thing, right? And the question is just, if you put number symbols in that far right column, do the pivots go over into that column or not? And if they don't, in other words, if the matrix is consistent, then S spans V. Right, so that's what you're looking for. But when you're checking the linear independence question, you're doing almost the same thing. You're actually just laying the vectors into the columns of the matrix again, but this time you're augmenting the matrix not with number symbols, but with zeros, right? Once you do that, then the issue is no longer whether this is consistent or not, but rather what's of importance here for the Li question is, are there any free variables or not? And you don't want those free variables, right? You do not want them. Li requires that there be no free variables. In other words, that there are no columns without pivots. Remember, every time you have an unpivoted column, that gives you a free variable, right? Which is a bad thing. That's a bad thing. That means there's going to be linear dependencies that you can write down, which you don't want. That means it's not efficient. It's not cheap. So you would like there to be no free variables. But the beauty of this two-part definition here, guys, is that you can check both of them essentially at the same time. And you saw me do that, right? On Tuesday, I put like 0/number symbol in that far right column, just to sort of multitask and check off both of these questions at one time. Yes.
Can it still be consistent if you have a free variable?
Yes, it can be. Like that would be true here, of course, because you would certainly have, this will always be consistent. If you have zeros in that far right column, then you would never have a pivot over there. So it's this second matrix is always consistent, but it may or may not have free variables.
Well, I meant for the first, like for S spans V, like if you have a free variable within your matrix, would that still be consistent?
Consistency depends on what's going on the far right column. It has nothing to do with whether there's free variables or not. You could have free variables or not, but if there's a pivot way over here, it's bad news. Yeah, good question. Okay, so this is the idea of a basis. Unfortunately, on Tuesday, I only had time to do one example, which was the vector space of R3. And I wrote down this exact example here. S has these three vectors in it. And I said, yes, they are a basis. And the way we checked that is we laid those vectors into the columns of this matrix here. Notice that I augmented it with both zero and number symbol at the same time, because I'm addressing both of the 2 points at the same time. And with a little bit of ERO work, the pivot configuration is going to end up like this. And if it ends up like this, you see that it is consistent. There's no pivot in the far right column, and there are no free variables. So that's a win-win, right? Consistency means it spans V. No free variables means it's Li. Absolutely true. So that is an example of a basis. But it turns out, guys, and you guys noticed this and somebody asked me about it on Tuesday, that because this is a square matrix right here in front, in this case, instead of doing the EROs, another way that you could have worked on that problem is you could have simply taken the determinant of this matrix and it would not have been 0. The determinant of that coefficient matrix would not have been 0, which is basically just saying that, yeah, if you do perform the EROs, they're going to make pivots that look like this. Remember, guys, if the determinant was 0, then you would have gotten a row of zeros on this bottom row, and that would have put a pivot over here, and it also would have created a free variable. And that would have been bad, right? That would have been bad in that case. That's if the determinant of A was 0. Remember, guys, good goes with good in this class, and bad goes with bad. So if the matrix is invertible, that's a good thing, and everything from that is also good. So including the fact that those columns make a basis, right? So actually, how many bases could you think of for R3? The answer to that is as many bases as you want based on just making a 3x3 matrix that is invertible. The easiest one would have been to make the identity matrix here, right? That's definitely invertible. But I could have done this one here, 1, 2, 4, 0, 3, 5, 0, 0, 6. That's also invertible because the determinant is not 0. So it's just there's as many bases for R3 as there are stars in the sky, right? You just make up vectors such that the matrix is invertible. And there's lots of invertible matrices out there. As long as the determinant is not 0, you have an invertible matrix. So my goodness, there's just a truckload of different bases for R3. There's so many of them. Now, a comment that I made on Tuesday is that although there could be many, many, many bases for a vector space, they always have to have the same number of vectors. So if I give you 2 vectors in R3, no chance they could be a basis. Or if I give you 4 vectors in R3, no chance they could be a basis. Every basis, as you can see from these examples, every basis has 3 vectors in it. So if I have too many vectors or not enough vectors, you don't even have to take a breath. You can just tell me right away, oh, that's R3, you only gave me 2 vectors, not a basis. Or that's R3, you gave me 4 vectors, not a basis. It has to be the correct number of vectors. But just because the number of vectors is correct does not guarantee that it's a basis. Because of course, if the determinant of that 3x3 matrix was 0, you would have still had to say, no, it's not a basis, even though it has the right number of vectors. Am I making any sense at all? Yes.
I have another question. So if you find out that the matrix is invertible, does that mean that basically the S does span V? Or
yes, if it's invertible, that's what we've been saying. If it's invertible, then it is a basis, which means S spans V and S is Li. Absolutely true. Yep. Let's do a different vector space example. Let's suppose that I took V to be, oh, actually, so sorry. Before we do another example, let's get a definition up here. Let's get a definition going here first. So the definition, the number of vectors in any basis for V is called the dimension of V, and it's just written dim of V. So dim of V, the dimension of V is just going to be the number of vectors that it takes to make a basis for V. So let's get right into our examples. You guys can tell me this right away, I'm sure. What is the dimension of R3 based on what we have here? 3. It's 3, right? The dimension of R3 is 3. And you can see every basis that's listed there has exactly 3 vectors in it. So now I would like to stretch your mind just a little bit and ask you if you think you might have a guess about what the dimension of any Rn would be. So if it was R4 or R5 or R6, does anybody have any thoughts about what the dimension should be, Dari?
N.
It should be n. That is exactly right. Actually, if you think about it, if I gave you less than n vectors or more than n vectors, you wouldn't even be getting a square matrix out of this problem, right? So like here, if I only gave you 2 vectors, the matrix would be tall and skinny. There wouldn't be a determinant that you could do. Or if I gave you 4 vectors, it would be wide and stretched out. Again, if it's not a square size, I can't even take the determinant to even have a chance of having an invertible matrix. So the only way to even have a chance of having a basis for Rn would be for me to give you n vectors. Otherwise, I'm giving you not enough or I'm giving you too many, right? And there's always sort of an exact right number that we should have. Okay, so that seems pretty reasonable. Let's go another step further. I'm wondering if anybody might have a guess for what the dimension of the n by n matrices should be. Now I'm getting away from just our very comfort zone of Rn, and I'm thinking about n by n matrices. If we need kind of an example to be thinking about, M2 of R would have been, the set of 2 by 2 matrices would look kind of like this. The question would be, how many vectors do you think it's going to take to make a basis for that? Oscar? Would it be n? Is that what you were going to say?
I was going to say n squared.
N squared. Is this going to take 2 vectors? So this is M2 of R. How many slots do you have here?
4.
4 slots. Just like over here, the number of slots in the R3 vectors, they each have 3 slots. Right? So if I kind of think of it that way, if I kind of think of it in terms of how many slots there are, I would say there's 4 slots. Also, if I was going to try to find a spanning set for this, the way you would find a spanning set here is you write down the general form, which I already did. Then the second step was bust out the variables. Bust out the variables, right? So it's going to look like this. So this is how you bust out the variables, which we practiced before. Right? And then you make your list. Well, how many things are going to be in the list? 4 things, right? You've got 4 vectors here. So I would guess that the dimension of M2 of R should be 4. And in general, for any n by n size, Brandon, you want to give it a try? What would be the numerical value? N by n isn't really what we would say. What's the right word for that? Say again? Which would be what? This is n by n matrices. It is n by n, but what's that better known as?
N squared.
Thank you. Yes, that's n squared. That's what I was looking for. It's just n squared. All right, and that's how many slots you have in the matrix. So that would just be n squared, and that is exactly right. Yeah, and by the way, so yeah, let's just add to this example. This is actually the standard basis for M2 of R. it is just the set 1, 0, 0, 0, comma, 0, 1, 0, 0, comma, 0, 0, 1, 0, comma, 0, 0, 0, 1. That is your standard basis for M2 of R. And you can see, sure enough, yep, there's 4 vectors there. If there had been, if this had been 3 by 3 matrices, you would have been writing down the form using 9 different letters for the 9 slots in the matrix, and you would bust those out and get a 9-dimensional vector space. Guys, this dimension is somehow measuring the size of the vector space. That's the intuition behind it. It's the size of the vector space. Questions so far? You feel pretty good about this? What about if it was an M by N matrix? So if I took the M by N matrices, anybody want to try a guess on what the dimension of that would be? Let's say they're 2 by 3 or something like that. So it doesn't have to be square size matrices, but what would be the dimension, do you suppose?
Right.
M times N. Yes, Mn. Because that's the size of those matrices, just M times N. So if I give you the universe of 2 by 3 matrices, well, that's going to be 6-dimensional. Absolutely true. Seem reasonable? Of course, if you were wondering, well, how do I know for sure that this is a basis? Well, you would do exactly the procedure that I reviewed over there. You would take each vector and lay it down into a column. First matrix goes in the first column. Second matrix would go in the second column. Third matrix would go in the third column. Fourth matrix would go in the fourth column. And then, of course, over here we have our 0/number symbol. But again, look at your matrix here, guys. It's a nice square size matrix. You can take the determinant of it. It's not 0. So that means that it will be a basis, right? If the determinant is not 0, you're going to have a basis there. So it's the same comment I made before. How many different bases could you have for these vector spaces? The answer is truckloads and truckloads and truckloads of them, right? As long as when you lay the matrices out into this bigger square matrix, as long as this is invertible, you're going to have a basis there, right? So you could make millions of different bases for M2 of R, but they would all have 4 vectors in them. By the way, there's another theme you might be noticing, which is it seems like the number of vectors that's in your basis seems to be matching up with the number of free variables when you wrote out the general form. You see that? For every free variable you have in this form, you're creating one of your basis vectors. So that's another way to think about the dimension of V. It's going to be the number of free variables in the general representation of that vector. With that in mind, I'm going to try another one on you here. If you kind of buy into that idea that it comes down to the number of free variables that you have, let's think about polynomials now. Pn of R. And I'd like to take a guess as to what the dimension of that would be. If we wanted, we could take a second and just think about P3 of R, just to give a specific one. I think if I write down the general form in P3 of R, the general form is basically a cubic polynomial. So my P of x would be ax cubed plus bx squared plus cx plus d. Does anybody have a guess as to what the dimension is going to be for this universe? Oscar?
Would it just be R2?
Okay, I need a number. I need a number here. Aiden? Let's do it for P3 of R first. Let's get real specific. It has nothing to do with powers of n. Brandon? I would just say 4. Yes, this would be a dimension of 4. If I bust out my variables, they're already busted out. And if I write down the vectors that are left behind, this is my basis, guys. It is just x cubed, comma, x squared, comma, x, comma, 1. For this, 1 second. Yes, I'll let you answer in just a second. But does everybody follow this? That there's 4 vectors here. Now, again, if you lay them into your matrix to check if these are a spanning set and if they are Li, then each of these polynomials goes into this matrix in a column. So x cubed might be 1 x cubed and then no x squared, no x, and no constant term. And x squared would be no x cubed term, but 1 x squared term, no x, and no constant. And you would do that all the way across, and look at this, you're getting a nice invertible matrix again. So this matrix has a determinant that's not 0. I don't know if do you remember the one, let's write this down as well, as long as we're talking about P3 of R. Do you remember the one from that video that you took some notes on a few days ago? It was one that I did as an example in my video, and it was the basis of 1, and then 2 plus 3x, and then 4 plus 5x plus 6x squared. And then I gave you 7 plus 8x plus 9x squared plus x cubed. So I did a little video on that one. And you guys watched it, took notes on it for the homework you just turned in 2 days ago. If I lay these 4 polynomials into a matrix, the 1 goes in just like that.
Oh, yeah.
I did this in the video, right? 2 plus 3x just goes in like that. 4 plus 5 plus 6x squared goes like that. And then the last one is 7, 8, 9, and 1. And if you just glance at this, you see that it is, upper triangular, and your determinant is not 0, right? So that is, again, a good thing. Good goes with good. If the determinant is not 0, then the vectors that you created that matrix from are a basis for V. Is everybody with me? By the way, this is the standard one. So every one of these vector spaces sort of has a standard basis, which just means it's like the most obvious, simplest basis of all. But doesn't mean it's really better than any other basis. A basis is a basis. So there can just be lots of right answers. Okay, how many people, before you tell me, raise your hand. Do you think you have a guess for the dimension of Pn of R? Okay, got a few people with their hands up. I'm going to let Brandon take it away. What do you think it is? N plus 1. Is that what the rest of you guys thought? N plus 1? N plus 1. It is N plus 1. That is actually the right answer. It is just 1 more than the power of the polynomial. So if I'm looking at cubic polynomials, I have to have 4 letters to describe it, right? I have an x cubed term, an x squared term, an x term, and a constant term, right? And if I was to go to, say, P4 of R, well, then I would just add 1 more term, which would have an x to the 4th on it, and the dimension would just go up to 5. It just kind of creeps up that way. In your notes, guys, on these examples, you should probably write yourself a note to memorize these. You really, 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 really want to know those values, okay? Because somebody's going to come along and hand you a set of vectors and ask you, are they a basis for that vector space? And if you know ahead of time how many vectors are supposed to be in a basis, that gives you a big leg up. That gives you a good advantage, right? So I want everybody to know these dimensions. Just kind of commit those to memory and be a good thing for you. Okay, now we have other vector spaces besides these. We have the vector space of n by n symmetric matrices. We have, I think in class about a week ago, I did polynomials in P3 of R where P of 5 is equal to 0. And so I can throw extra constraints in here and kind of give you some weirdo example that you never thought of before. Well, obviously you won't know the dimension of that ahead of time, but these you should know ahead of time for sure. Just have those memorized, guys. You'll be really happy and you'll thank me later. Okay. I want to put all of this together with a quick little chart to help you decide whether a set of vectors is going to be a good candidate for a basis or not. And so this next thing I'm going to write down would be really good for your notes, I think, and just a good summary. Okay, let me put it over here. So I'm just going to call this a little summary. And then this will pretty much wrap up this section, and then we can spend some time looking at some homework problems. So let's let V be a vector space. And I'm going to just assume that the dimension, well, let's just leave the dimension of V out of it. So I'll just call it dimension of V. And then I'm going to take S, and I am going to use the set V1, comma, V2, comma, dot, dot, dot. Please take careful note here. I'm going to use a VK for the last vector. The reason that I'm changing, you might wonder, why are you changing it to a K now? I thought we were always calling it Vn. Well, because I've got all these n's now in my dimension values, and I want to imagine that somebody comes along with a set of vectors that is just a random set, has nothing to do with the dimension of the space, okay? Now, what I'd like you guys to do is make yourself a table. So give yourself plenty of room here, guys. I'm going to fill up this entire whiteboard here. I'm going to make a table with 3 columns. And at the top of each column, I'm going to put something. The first column, I'm going to write K is bigger than the dimension of V. And then in the middle column, I'm going to write K is less than the dimension of V. And then in the right column, I'm going to put K is equal to the dimension of V. So somebody hands us some vectors, and the number of vectors that they hand us, I'm just going to call that K. And this is why you want to memorize these dimensions values, because then you'll know which column you're in. If you know what the dimension of V is, right, then that's really going to help you with this. K is something you just glance at the set and you'll know what it is. Like, oh, how many vectors did they give me? It's all you have to know. So here is the scoop. Here is the scoop, guys. If K is bigger than the dimension of V, then that's too many vectors. That means you don't have a basis, right? In both of these 2 columns, you do not have a basis. But I would like to be specific about what goes wrong. In this first column, when K is bigger than the dimension of V, S cannot be Li. There is no chance of that. And underneath that, I'm going to write it might span V. You would have to check this one. You would have to check that out and see, well, you know, with the tests that we had earlier, lay the vectors in the columns and see if it's consistent or not. But do you know why there is absolutely no chance that these vectors could be Li? It's because if K is bigger than the dimension, then when you go to make the matrix, it is going to be a wide, spread out matrix. It's going to look like this. It's going to be a wide, spread out matrix. And if you write down sort of where the pivots might be, guys, remember, you're only allowed to have pivots 1 per row at best. At best, 1 pivot per row. And you have more columns. You have more columns than you do rows, which means you must get free variables. It's not even a question. If your matrix is wide and spread out, you will be guaranteed to get free variables. And if you just remember from the recap a few minutes ago, free variables means it's not Li. Okay, so it's game over here, guys. You do not have a basis. They are not Li. They might span V. That is possible, but there's no guarantee of that. If you're looking for an example for this, okay, so maybe I need to extend my, do you have room to extend your columns a little bit? Let's add just one more thing. Let's keep these, I'm just going to continue these 3 columns right here. I'd like to give you an example of that scenario that we've already done. We did it on Tuesday. An example for this case where K is bigger than the dimension would be to take this set. Do you remember this from Tuesday? The set of 1 plus x, 1 plus x squared, 1 plus x squared plus x cubed, and x plus x cubed. We did it 48 hours ago, right in this very room. And you can see that the K value, how many vectors are there here in this list? 5, right? So K is 5. But then what's my universe that my polynomials are coming out of? That would be P3 of R. This is why you want to know these values here, guys. What's the dimension of P3 of R? Only 4, right? According to the formula here, the dimension of P3 of R is only 4. So that is K bigger than the dimension of V. These vectors cannot be Li. So let's call this S. S equal to that set. S is not Li. I actually don't even have to set up the matrix. I can just look at this. Oh, 5 vectors. I'm in a 4-dimensional space. No chance. Okay. It's too many vectors. Too many vectors, and we can just say that. Right. Now, these vectors, the question would remain, do they at least span P3 of R? For that, you would have to set up the matrix and make sure that you get it into row echelon form and see if there are consistency. See if the pivots go into that far right column. I think in this case, this is a spanning set, but it's not Li, and so it's not a basis. So if it's not Li, then it's obviously not a basis either. What we're going over right now, guys, this is bread and butter vector space theory. You will definitely want to get this stuff down solid. Super, super glad you guys are here today because this is a really, really important one. Okay, let's do another scenario. Except I got to find my example that I'm going to use. Oh, there it is. Okay, so let's do K less than the dimension of V. In this case, guys, if K is less than the dimension of V, I can tell you that S cannot span V. Cannot span V, and I'll add over here in parentheses, it might be Li. It might be Li, but guys, it's already game over if you're looking for a basis. It will not be a basis. It's not enough vectors this time. This time, if I set it up into a matrix, what will happen this time, guys, is I will get something tall and skinny. This is going to be the tall and skinny outcome here. And what's going to go wrong this time is that even if your pivots are looking pretty nice, remember that below your pivots, you have to have nothing but zeros, right? Which means on these lower rows, if the matrix really is as tall as I'm trying to get you to understand, then you are for sure getting a pivot going into the far right column here. Again, I don't even have to actually set up the matrix to figure that out. I can just look at it. Okay, the number of vectors compared to the dimension of V is not enough. And we did an example of this on Tuesday as well. Let me write it down. Let's do an example for this column as well. So for this column, we could use the example S equals, excuse me, S is equal to the matrix 1, 0, 1, 2, comma, -1, 1, 2, 1, and then comma, 2, 1, 5, 7. All right, my column is a little bit narrow. Don't have enough room to write the whole thing out, but it's pretty decent. So that's your set. So we did this one on Tuesday. What is my K value for this problem? What is K? K is just how many vectors did I give you? 3, right? There's 3 matrices, so K is 3. And then what is the dimension of my universe? You can tell by looking at the matrices that we're looking at the 2 by 2 matrices universe. What was the dimension of that? 4, right? Okay, so there you go. K is less than the dimension of V. So we already know that this set S cannot span V. S cannot span M2 of R. It cannot do that. There is no way. Even without taking a breath, I can conclude that. Yeah. Now, again, there is a chance that these vectors might be Li. That's the maybe part. I've got it here, right? They might be Li. If I wanted to know, are they Li or not, I would lay these 3 matrices into the columns of a matrix. I would augment it as usual, and I would do my EROs and see if there are any free variables. But actually, of course, we did that on Tuesday, because this was an example that we did on Tuesday. And what we saw on that example on Tuesday is actually these vectors are LD. They are actually LD. And in your notes from Tuesday, you would see that. For all of these examples, guys, they're just going back to 2 days ago and just referring back to something we did before to kind of tie it all together. So this is a really lousy set of vectors. First of all, they don't accomplish what we hoped, which is that they don't span our vector space. And then not only that, we spent too much money on them. We spent $3,000 on these vectors, and we found out later that actually these are LD. Okay, so that is pretty bad as well. But in any case, this is, again, not a basis. It's not a basis. So you'll see all of that in your notes as you review. Okay, the last case, let's finish this column, and then I'm going to let us move on to more practice on this. What if K does equal the dimension of B? Well, I already made the comment before that that does not guarantee that you have a basis. It might be a basis, but what I can tell you is that S is both or neither. You remember our 4 outcome scenario? Is S Li? Is it a spanning set? Is it both or is it neither that we did on Tuesday? And what I can tell you here, guys, is that it is both or neither. It cannot be one without the other. Okay. In this case, your matrix will be absolutely perfectly square. So if I set up the sort of the shape of the matrix here. So if I just set up that matrix A like that, this is absolutely perfectly square. I'll just say n by n. It's a square matrix. And what I can say here, guys, is that it is both if the determinant of A is not 0, and it is neither if the determinant of A is 0. If the determinant of A is 0, then it would be neither. So it's either both or neither. Guys, of course, guys, when I say both, that means basis. A basis is the outcome where it is both a spanning set and Li. Okay. So I think we're really getting this summarized nicely by this table. If I wanted an example of this, well, we've already got examples, but we could do example. Yeah, so let's just do S equals, 1, 0, 0, 0, 1, 0, 0, 0, 1. And we've already got this in our notes. I'm just kind of writing it down again. When you put this into a matrix, you just fill those columns up with those vectors And that is an invertible matrix. It has a determinant that's not zero. And therefore, because of that, then in this case, S is a basis. It is a basis. In fact, it was what we called the standard basis for R3 in this case. But if I made another example, I'll just do a second example here on the same column. Let's say that I gave you the set of 1, 1, 1, 2, 2, 2, 3, 3, 3. I need just a little bit more room, guys, on this third column. I've got to make it a little bit taller. On that second example, so this is just a new example. I'm just putting 2 examples into this column here. On this example, when you build the matrix A, remember you're laying the vectors vertically. So the first vector, 1, 1, 1, goes right here. The second vector, 2, 2, 2, goes right here. Third vector is 3, 3, 3, goes right there. Is that invertible? No way is that going to be invertible. I can already see an ERO that's going to give me a row of zeros, right? So this is not invertible. The determinant of A, in this case, is 0. And so this is S is neither. It's not a spanning set, and it's not Li. Remember, guys, that Li would have meant no linear dependencies. Well, I can clearly see these are dependent. The second vector is just 2 times the first one. The third vector is 3 times the first one, right? It is possible to write one of those vectors in terms of the other. You're spending $3,000 here when you really shouldn't have been spending that kind of money. And what are you getting for your $3,000 right now? Well, you spent $1,000 on this vector right here, this marker. That's the vector 1, 1, 1. And then you spent another $1,000 to make the vector 2, 2, 2. Notice it's pointing in the same direction. And then you spent another $1,000 on the vector 3, 3, 3. I love this. Nice little prop I have here, right? All 3 of these vectors are just pointing on this line. Like if I ask you what's the span of these 3 vectors, it's not very great. It's just the vectors that are basically pointing in this one direction of this line. And you're like paying triple money to span the line, while in the meantime, you're not spanning the rest of R3 at all, right? Anything that's off of this line is not being spanned. That's kind of the scoop on that. So are there questions on this? This table, this 3-column table, which unfortunately got spread out on the 3 boards, is a really good thing to kind of keep coming back to. The only thing is, the table will be useless to you if you don't know these dimensions, right? You have to know what the dimensions are to know like which column are you in, right? So you're going to need to know whether you're in a 4-dimensional space, and then what K is easy. You're just counting how many vectors were given to you, and you can answer that. Okay. The other thing is that, oh, sorry, Aiden, go ahead.
Can you explain again why for K less than the dimension of why it might be LS?
Why it might be Li? It's because it is possible to have the pivots look like this, where there is no free variables. So remember that Li was the situation where you do not get any free variables in those columns, and so that could happen here. Whereas when the matrix is wide and spread out, you must get free variables, which is kind of the bad news outcome. Yeah. Okay. All right. I have a little group work here for you. By the way, this table is great if you know the dimension of V. If you don't know the dimension of your vector space, it's not nearly as helpful as you would like to think. So I'm going to go ahead and let you guys work for just a few minutes on these 2 questions. That's based just on what we've just been talking about. And I'd like to get groups of 3 or 4 of you, and you can use the whiteboards all around the room. Sorry, pass those back for me. And I'll come around and give you guys Thank you. Okay, guys, once you've got a handout, come on up. Let me get this erased first. Oh, you want to help me with that? All right, you guys ready to rock and roll? Yes. That's that. Sorry. Good. Very good.
Lives, like you've been. No, you have to ask people.
We can just erase this. Get that out of your way there. Sorry. You guys want to join them? Yeah. Okay, great, great, great. Good.
Are you doing on this material? Okay. Maybe you guys should take a lead.
Matrix rows and
generically.
how can you write a general form?
Yeah.
Where the rows.
By three matrix, rows add up to zero. You're gonna be using letters. Using letters. Talk to your partner for that.
Grammar was like.
Yep. You said we're all rows added up to, so row.
Nice. Guys, good job. It's great. Are you guys working on number one? So number one, this is a slightly different problem. This is not finding a basis or anything. I just want to know, like, what the form of a 2x3 matrix is where the rows would be adding up to zero. So let's get rid of that augmented column completely. You don't want it. We just want a 2x3 shape of a matrix filling in with letters.
You guys can correct me if I'm wrong.
That is looking really good there.
Thank you.
Minus.
Nice, nice, nice. I would recommend you plug the C and the F into the matrix, but otherwise it's perfect.
Yeah.
Perfect, perfect.
You know, I did.
This is our hardest part of this problem. Writing down. Once you have this form written down, the rows are adding up to zero. Now you're gonna go into the variable. See if you can do it.
It's gonna be.
Guys, I'm not asking you
Oh, yeah.
about
Dimension.
I just want to know.
I don't know.
Here. The second problem would be more about what I was telling you. This one, I want to say. Okay, so you got four variables, I think, in your matrix. Let's bust those.
I'm running it so big.
Bust out the variable. We don't need to automate. Each one is different. No automate. Just write it down. A, B, and then negative. B. No, that automate is zero gonna be like your list. We don't have to.
Now we need what? Do what?
Anybody need help?
Bring strengths and
Oh, yeah, that's
so that
super-
the.
Super good.
And then just be the.
I get it.
Yeah, you have to factor it out.
The second step is.
Then they all have to be 2x3 still.
A, B, C.
So we would only get, you'd get.
Oh, I see. Oh, I thought you were putting this in.
It'd be A.
Oh, okay.
There'd be four terms though, right?
What if you thought? If I was to make all in, I wasn't sure.
So you'd end up with.
Okay, thank you. Yeah, how are you doing?
And it'll be a 2x2 matrix.
Not right now, we're not
And then-
actually working on this perspective.
Yeah, I know.
You're working.
And then.
So does he not gonna make money?
No, I don't like this.
I don't know if it's gonna be down there.
This one.
Yeah.
And so I want you to take this form and I want you to.
And then it'd be. Oh.
Anybody need help? Correct answer. Yes, that looks perfect. That is perfect. Great, so this is a four-dimensional subspace of what would have been the six-dimensional arrow 1 by 3.
Vector space.
Right.
Yeah, negative.
So part
Now, earlier today, the dimension of 1 by 3 of R.
Circle the correct.
By these numbers.
That's not
But
longer.
we're not working on that, we're working with this thing.
Now it's there.
There you go, there you go.
Dimension of that is on the flip, because you've got your.
Oh, we need one.
So it's a subspace. That makes sense. A subspace is smaller than the big.
So we talked it out. We're just.
So I can't
making
make anything.
Every circle that they.
Go, I basically said, look at it as a spanning set, then backwards it's a subspace. Basically what it is that E is equal to the span of these four things.
Essentially.
Any
From what I remember.
span of anything.
Because we have to like.
So you can avoid, I mean, if I wanted to do closure under addition, I would take this thing and then I'd have to come over here and take like another lateral, I'd have to do another one.
Only
Same thing, and then I would have to actually add them together, and it would just be a little bit messy. But it was, yeah, make sure it has the same form again. So this is much faster, and not only that, as a byproduct.
You guys wanna get started on the second?
So faster, you actually drop the standards that were in the process, which is kind of a double win.
Let's try to start. You start writing it out. On my paper.
Hey, this is the right answer. Well, that's basically the answer, because what this means, if that's the Spanish practice, this means is that the V that they gave you in this problem is the span.
Or how about your pitch on that was
It's the span of.
pretty sure.
That allows you to avoid having to go through the pain.
I'm pretty sure it's like this hand.
Over under it. Oh, exactly. In order to do that, you have to come out
That'll be the answer.
and write out a whole.
So next-
That's not the same.
Well,
Answer. Exactly, so that's in C, that's in B, right, and then you have to add them together. It's not hard. This is the fastest. Basically, in the process of.
S means the S.
What is that like?
When you're.
Find
in- So we have to-
For the
we
very.
put these in the papers. We do EROs this way.
I think it needed L. I think that's why. I'm not sure if it's Spanish.
Yeah. Well, yeah, I think we do. We speak up the call.
The number of terms is equal to K. So this
When you have.
K,
Because I have to.
that's right. K equal to dimension.
Well, then you would have had to write down your
That
matrix.
means that's either both or neither.
And then you would have bumped it up. And you would have gotten-
I can't feel it.
And that's actually not the dimension of much.
Yeah.
But it's not like you need
The dimension of it is what?
Because we can do both right here.
The dimension of this thing.
So you convert it into.
Yeah, you can get into total matrix and then you can just. Can't be as.
Wait, so what did you say? Oh, echelon, or like ERO?
Yeah, so this is a.
So-
six dimensional.
I'm just gonna be arrow. Probably there, right? It could be.
Dimension and.
But.
What the determinant is this?
Systems.
Oh, you-
If we can actually do it.
Rows out of-
But it doesn't matter. I do remember if you do it. It didn't matter as long as you're consistent. So it doesn't matter actually. As long as it's six, you can do that however variables are. No, seriously, you can do it like this, like 50. I think you're consistent with each. It's equal, and other. Yeah. Yeah.
Of course, yeah, to be such that that. row-
Oh, the Arrowman?
So if you're ever gonna do it, you have to make sure you do it all the time.
So when you think about dimensions.
Let's see, take the 24, 1, so negative 28. Negative 6 plus zero, minus 24.
Right, if I didn't have the condition.
It's square.
So it also had a- Yeah, so it would have been this.
Right.
And then a larger.
You would be in this dimension of forties.
Correct.
It's 3 by 3.
Yeah, no, that's great, that's great, good job. See if you can do number 2. Is it okay?
Now you go.
That looks good.
That's 2, 2, 1. You take these become the columns. Yeah,
Yeah, so I can see how this is right here. It's 3 terms.
Including the zeros, yes. What about the side?
X squared.
Yes.
Yeah, so I would take the 0 x
So,
minus 6 squared.
you
You just throw it in.
Sweet.
So yeah, that's why that's why my belt was like.
Oh, no, you build it
I was thinking
vertically.
What's faster?
Yeah, you put.
Oh, that's
you put
true.
these terms-
Why would you when you from one where it has to be out of. I didn't think about it.
We're in the scenario. Either K is 3.
for stuff.
1, 2, 3, right? So that's the third column of that table we just drew. So that means it's both or neither, and it all just comes down to. But I would just leave it. Yeah, the arrow method. Anybody need a hand?
78.
This is looking really good, guys. Nice job on that. So the point is now that this V is the span of those 4 matrices.
Yeah.
And that's why it's a subspace. Anytime you take
Oh,
the
yeah.
span of
You
any.
told me I was too now.
Always do this. So this is a subspace. What's the dimension of this subspace, by the way? That's not the subspace. I'm talking about this subspace right.
So this is not a square matrix.
Just look at it.
Does not matter. So it's longer horizontally, meaning already
Well, what's the, say it again?
it will not be
Right.
but it can.
1, 2, 3, 4. Yeah, exactly. This was 6. So within the big 6-dimensional universe of all 2 by 3 matrices, here we're looking at a 4-dimensional. So this.
Yes.
That's it. Thank you. Yeah, you're welcome. Good job. Anybody need help? You guys are doing great.
Yeah, -6.
Something's wrong here. There's too many variables.
1, 0, 2.
No, now we do this. Make sure it's not 0.
Get it just over to the 0. That's the right answer. That's the right answer. That looks really good. Stop. A value equals 5.
Oh, yeah.
The first column. Cannot be allowed. Minus
Span.
0?
But
That makes sense.
span Yeah, now you're gonna.
Yeah, I
fill out
believe that's what I got.
Yeah, exactly.
So for A,
Anybody need help?
In order to span.
I would.
78, yeah, 78 minus 24.
You are in the rest.
Matrix,
221.
you put a matrix in a matrix.
221. And
So
then
this
it's
one.
vector.
Oh, negative 24.
Three.
Notice that there's no.
We're following the matrix right here.
Minus one.
Because if we're saying that if one K is greater than 13, it has to be long. The vector would have to be like that. It has to be long, so it was.
At all actions.
Oh, I found it. We just have to make sure.
Yeah.
Oh, you forgot this mason. This one is not going to be a square range. So that one, you'll have to solve a little bit differently. I know. You were close.
Zero.
Let me know. For this year.
Either.
You already know. You're trying to expand. Expand it.
You're in, or you're in. So you know,
Great. No. Sorry. So that'll be that one.
Okay, now we have to do B.
That's why you wrote not LI, because there's guaranteed to be a free variable, because this is a wide spread out matrix. The question is, will it actually span the space? You could do all of the EROs, or you could maybe get lucky and.
Even though K, well, actually, because K and.
It's kind of a trick to save you a whole lot of years, and if you don't see it, it's not a big deal, but it'd be worth looking at it. Yeah, I think you're on this.
Because.
Look what you got.
So immediately, I believe so.
Back to the same.
But I'm not.
So when you do your euro, you have to remember, the one thing it is, you're setting up the statements, you should be augmenting it like this, yeah. If you do that, and then when you are here,
Neither and neither?
you realize, oh, we
These
got a row
become
of
like
zero.
problems.
Although you want to be a pivot there. And now it's not, not a standard.
I'll try on that.
Already not.
They were gonna
Because.
Oh, I
No, I
The
The dimension here is only 4.
Oh.
So this is bigger than this, so it's not LI, it might stand the space. All of shows here that actually.
So it's 1, 2,
So this
2,
would be
1.
3.48.
If you want to go ahead and take a short break.
Zero.
Time to-
Negative 3, 0.
Guys, whenever you get finished, you're welcome to take a break. We're gonna take a break and then we'll come back and look at some of the homework after the break, okay? But everybody's doing a great job. Anthony, that is right on the money.
They're not.
All right, not LI. It's not LI just because K is bigger than the dimension. And then getting that pivot of the heart. Seals the thing. You got here on that one. Good job. Good job.
No, it's not 24. So it's wider. So because it's wider than something, there are things that the rest has to be. So K is and the dimension. K is greater than the dimension.
It's like a bad set of vectors. So
Expand the base.
you didn't even span the space. Absolutely.
That's either neither or it's.
Remind you. This will help you. Here.
Mine is this.
But if you have that flow in there, that really helps you see how there's the pivot going.
Yeah, those are.
It's not consistent, right?
Oh, I've seen this before.
Yeah.
That's factorial. That's like,
Isn't that both of these problems. Okay, guys. Certain lights, and then we'll come back and go some wisdom this here.
Guys, if you haven't finished yet, this would be a good time to take a break because I'm only gonna give you about 5 more minutes.
This determinant should have been zero.
Yeah.
It should have been zero.
Oh, I know what the problem is. Negative 48 minus 6.
Oh,
To add that up, you do get 12. And if the determinant is 0, then. That's it. That's it.
Yeah. Can you check ours?
Yes. Yes, this is absolutely right. You have your row of zeros here, which puts a pivot over there. It's obviously too many vectors, so it's not Li. Here you found the determinant was 0, so that's also neither. They're both neither. That's good. That's good. Nice job. Nicely done.
Oh, because we know that if we combine these with operations.
Yeah.
we get zeros.
Oh, they're gonna be one row. Oh, I
And there's gonna be some random number there that.
Yeah, that's it. That's it.
Yeah. So you can move it
Thank
to
you.
the
Yeah, that
bottom.
looks great. Yes, K is just, you literally just count how many vectors did they go on. Exactly, really, really good. Oh, thank you, thank you. Are you just now getting here?
Yeah. I've been blocking you.
Oh, I see. If you'd rather, you can come back at 1 o'clock and see the whole thing. But if you can't come at 1, then you'll just have to watch the video later. Yeah. That, we did do that in the first part of the class today.
Thank you.
Yeah, you're welcome. Thanks. Yeah, no worries. All right, everybody. Thank you for your work on the group work. I think most of you finished. This group work, though, if you didn't finish, or even if you did, just a quick reminder, the solutions are in Canvas. So you can always review these a bit on your own time, and definitely would recommend doing that. But hopefully it was helpful, kind of practicing how to use that chart that I gave you to understanding this stuff a little bit. I'm going to spend, we got 35 minutes of time left today. I'm going to spend about the first half of it covering 2 more sections in the book. And then I'm going to spend the second half of it hopefully starting to do some of these homework problems for Friday with you that are due on tomorrow night. We're skipping section 4.7 completely. So don't have to worry about that. And we're finally going to start pulling ourselves out of the abstract abyss that we've been in with this these ideas of linear independence and spanning sets, and talk about something that I think is a little more down to earth. This is why I can cover 2 sections in 20 minutes, basically, which are 4.8 and 4.9. Which is getting to the end of chapter 4 here, actually. There are 3 important subspaces that you can always associate to any matrix. And I just want to go over these with you. The first one is actually one that we've already talked about, which is the null space of A. So the first one is the null space of A. So A is M by N, right? And the null space of A, let me just remind you what that was. That was the set of vectors, I'll call them X, in Rn, such that A times X is equal to 0. So you've already had some homework on this. So I could ask you to find a null space or find a basis for a null space. And I think you guys could all do that. You basically just solve this system. How do you do that? Well, you write down your matrix and you augment it with a column of zeros. You row reduce it, you circle your pivots, and then you just solve it by back substitution. It's literally, to find the null space of a matrix is something that we've been really doing it since chapter 2, right? It's just plug and chug. EROs, circling pivots, and back substitution, right? Notice that the set of vectors that are the solutions to that system live in Rn, which means, of course, that this is a subspace of Rn. It is a subspace of Rn in this case because of that. Let me just, even though we've done the null space concept before, I'll just do a quick example again, just to kind of get this back into your mind. Let's take this matrix A right here, guys. The first row is 1, 2, 6. The second row is 2, 1, 6. The third row is 0, 1, 2. And the fourth row is 1, 0, 2. Let's just say we have this matrix. What's the size of this matrix? 4 by 3. Excellent. And so the null space of A is going to be a subspace of R3, right? The n value is being 3 in this case. If I want to find the null space of A, as I was just describing, guys, we just do these EROs, okay? I'm going to skip the ERO details because it's kind of the boring part. That's not the concept I want to focus on right now. And I'm just going to go ahead and get the row echelon form immediately. Oh, I'm so sorry. Before I do that, I'm so sorry. I need to augment the matrix with zeros. Yeah, so for the null space of A, let me write that here. For the null space of A, I need to augment this matrix with a column of zeros. This is the procedure. So I should just recopy it correctly with a column of zeros on it, augmented onto the right-hand side. That's what I should have done because the right-hand side is the zero vector here. Now I'll do my EROs without really doing them. Just going to skip the details. You can see that the first row already has a pivot. I'm going to circle that pivot. Guys, if you're still not in the habit of circling those pivots, keep working on that because that really does help. I'll take the third row and move it up to the second row. And then I'm going to ask you to take my word for it that all of the other rows just get wiped out completely. So if you do the EROs, the third and fourth rows will completely get wiped out. And we have unknowns here, as always, that go with these columns. I'm going to call the unknowns X, Y, and Z in this case. And do we have any free variables? The Z variable, right? Z is free. Let's just put that here. Z, I'll call it T, which is free. And then if I solve by back substitution, so if I look at this second row, y plus 2z is adding up to 0. And so if I solve for y, y is negative 2t, right? So if I put in t for z, and then I solve for y, I'll get negative 2t. And then I have to solve also for x. So I'll go back to the first equation. X plus 2y plus 6z equals 0. And if I put in what z is, so I'll put a z equals t into there, and I'll put negative 2t for y. If I solve that for x, I think I'm going to get negative 2t as well. I'm kind of skipping the details a little fast because this is just back substitution, okay? So what is my null space of A here, guys? The null space of A is the set of the vector negative 2t, comma, negative 2t, comma, t, and this is such that t is in the real numbers. Okay. That would be the form of the vectors that are in the null space. How do you think I'm going to get my basis for the null space? Or in other words, my spanning set for the null space here? What's the new thing that we've been doing in chapter 4 that we didn't do before? Once we have this written down, the next step is to bust out the variables, right? In this case, I only have one variable. I'm going to bust that variable out. If I bust out that variable, guys, and just drop the t, this becomes my vector. This is the vector that basically forms the basis for the null space. So the basis for the null space of A is just this one vector right here. Okay? And so what is the dimension of the null space here? How many vectors are in this set? One. It has 3 slots. It has 3 slots, but there's only one vector here, right? It's only one vector there. The null space is one-dimensional. Just because it's a word that comes up a lot in linear algebra, there's a name for the dimension of the null space of a matrix. It's called the nullity of the matrix. I'm going to write that as a quick definition here. Right? So the nullity of A the nullity of A is the dimension of the null space of A. The nullity of a matrix is the dimension of the null space of A. So on this example that we just did, this is a matrix whose nullity is 1. Make sense so far? So this is a one-dimensional subspace of R3. Right, so in this case, n was 3. So it's a one-dimensional subspace of R3. And we've got one basis vector right here. Okay? Now, I would like to just try to understand, why did the answer end up being 1? The reason that the dimension of this null space was 1 was because we had one basis vector. Why did we only have, so just listen for a minute. Don't try to write anything down. Just listen. Why did we only have one basis vector? It's because we had only one variable to bust out. Why did we have only one variable to bust out? It's because, yes, we had one free variable over here in the matrix. We had one unpivoted column, right? Actually, the nullity, if you, now you could maybe write this down as a nice note to yourself. It's the number of unpivoted columns in the row echelon form of A. That is basically what it's going to end up being. It's the number of unpivoted columns in the row echelon form of A. And so now I think I'm ready to present to you all the absolute easiest theorem in linear algebra to understand. You ready for this? Do you remember, was there a name for the number of pivoted columns in a matrix? Oh, the rank, right? The rank is the number of pivots. And now we're saying that the nullity is the number of non-pivots. Oh, it's almost like they're opposites. Take a look. In this matrix, we had 2 pivots. The rank was 2, and the nullity was 1. But the point being, every column of your matrix is either going to be pivoted or not pivoted, right? And so if you add up the number of non-pivots with the number of pivots, it should add up to n. N, the number of columns in total. That is called the rank nullity theorem. It is the easiest theorem in linear algebra. I'm going to write it down for you guys. The rank nullity theorem. This is a famous theorem that is really, really easy to explain. And it just says for any matrix, A, let's say it's M by N, the rank of A plus the nullity of A always adds up to N. It always adds up to N. The rank nullity theorem. And so in our example that we just did, in our example here, we have a matrix that has a rank of 2. And the nullity, we worked that out, it was 1. And the n was 3. So the formula in this example would just go like that. 2 plus 1 equals 3. So if I have a matrix that has 10 columns, and I tell you that, let's say I tell you that the rank is 3, then you can already tell me the nullity. Got to make it add up to 10. So that it would be 7, right? 3 plus 7 is 10. Super, super easy theorem. Okay, so it's a nice one to know, though, because it allows you to figure out the dimension of the null space ahead of time. Okay. You see, that wonderful chart that I made for you guys a little while ago with the 3 columns. I keep saying this, but I'm going to say it one more time before I go on. This chart is only useful if you know what the dimension of V is. So sure, I know what the dimension of P3 of R is. I know what the dimension of Rn is, those formulas I asked you to memorize. But what if I gave you this matrix and I said, what's the dimension of the null space? All I did was hand you this matrix and I said, what's the dimension of the null space? It's not going to be so easy, right? We actually had to do this work and figure out what the dimension of the null space was. It was not clear just glancing at it from the beginning. Here we had to do some work first to see, well, how many pivots do we actually have? Turns out it's 2. All right, great. If the rank is 2, and I'm trying to figure out what's the dimension of my, space that I have so that I can use this chart, right? Then I can use that rank nullity theorem to fill in that number. Say, oh, now I know what the dimension of that is. So it's just kind of handy to make that connection. Okay, so far so good. Oh, it's like the 2x3 matrices whose rows add up to 0, which was what was on the group work, that first group work. I don't know what the dimension of that is off the top of my head. I have to start by writing it out. Oh, here's A and B and negative A plus B and C and D and negative C plus A. Oh, okay. So now I'm going to bust out those 4 variables and the dimension of this is equal to 4, right? But that's not just given ahead of time. We have to be able to come up with that. So I love this chart. And it's great when you know what the dimension of V is, but if you don't know the dimension of V, you have to figure it out first before you could take advantage of this. Okay, so far so good? Really quick, I would like to talk about 2 more subspaces. I've talked about the null space. Technically, we've known about that one for a while. I'd like to give you 2 more. So number 2 is something called the row space of A. The row space of A, and what is the row space of A? By definition, so this is actually the definition, I'm just going to put it as part of the equal sign here. The definition of the row space of A, my friends, is that it is just the span of the row vectors of A. If somebody asks you, why is that a subspace? What's your answer going to be? Because it's a span of something. Doesn't matter what it is, right? Anytime you take the span of anything, you always have a subspace. So this is automatically a subspace. The more, maybe slightly more interesting question would be subspace of what? So this is a subspace for sure, but it's got to be a subspace of something. So if I think about the rows of a matrix, so we've got our example here that we're going to look at. How many slots are there in each row? 3, right? And is that the M or the N? It's the N. It's the N. So my friends, this is a subspace of Rn again. Same thing as the null space. The null space was a subspace of Rn, and this is also a subspace of Rn. So let's just look at it for our example from the example above that we've just already been working with. So the row space of A, for this example over here on the matrix on the left, it's the span of, let's see, the vector 1, 2, 6. The vector 2, 1, 6, the vector 0, 1, 2, and the vector 1, 0, 2. So it's just the span of the rows of the matrix. So far, so good? So I have a question. would these 4 row vectors be a basis for that row space then? Would they be a basis for it? I think so.
Wait.
Well, what's the K value here?
4.
4. And these vectors live in R what? R3, right? So what's the dimension? So this is 3 dimension, right? So is this matching? No, K is too big. K is greater than the dimension of V. So in this case, they cannot be Li, right? This is too many vectors. We've spent $4,000 here. And we're only working in a vector space whose even the entire universe is only 3-dimensional. So this is actually not a basis. However, these 4 vectors, they are guaranteed to be a spanning set. Not for R3, but they are a spanning set for whatever they span. I mentioned this on as the idiotic comment that you can make. I said that on Tuesday, that a set of vectors is always a spanning set for whatever they span. So these are halfway to being a basis, but they fall short because they are actually LD. They are actually LD. And so how do we get the basis? So to get a basis, this is what you want to write down. For the row space of A, how do you find the basis? Well, this is quite nice. It turns out all you have to do is take the pivoted rows of the row echelon form. So to get a basis for the row space of A, you just take the pivoted rows of the row echelon form of A. This is the recipe. In other words, guys, what I'm kind of saying here is that I've got these 4 rows, and I know that they are LD. By doing these EROs, we expose those linear dependencies when we get these rows of zeros that come out. Essentially, the EROs are massaging this matrix. They're basically taking your 4 row vectors and they're playing around with linear combinations of them, and they're zeroing out some of the rows. And the remaining vectors, this one and this one, are the only 2 that have survived that massaging process, and that becomes your basis. So in our example, the basis for the row space of A is just 1, 2, 6 and 0, 1, 2. So we just keep, well, it's not surprising. We had 4 vectors here. Turns out at the end of the day, the basis was just 2 of them. Now, I'm not talking about a basis for R3. I'm talking about a basis for this subspace of R3, which is inside of R3 as the smaller thing that we're calling the row space of it. If I want a basis for R3, I would need 3 vectors, because we already know that the dimension of R3 is 3. But this is a row space that's 2-dimensional. By the way, that's another thing I should write down. What is the dimension of the row space of A? Well, if you look at how you're getting the basis for it, you'll have your answer. How do you get a basis for the row space of A? Take the pivoted rows of A. Well, that would mean that you're taking exactly as many rows as you have pivots. In other words, the dimension of the row space of a matrix, my friends, is always just the rank of the matrix. Okay? Is that working for this example? What was the rank here? On our example, the rank was 2. And how many basis vectors did I end up with? I got 2. Totally what we would expect. So it's interesting. The null space and the row space are both subspaces of R3, but one of the subspaces was two-dimensional. The other subspace, which was the null space, was only one-dimensional. Again, 2 plus 1, adding up to 3 right here. Yeah. Remember, when you do EROs on a matrix, there's many different correct steps to take. 30 people in this room, we could have 30 different correct row echelon forms. And that would mean that we could potentially, what I'm trying to get at is that this is not the only right answer. You could have done different EROs and come up with something else. But you would have for sure come up with 2 pivots. No matter what it was you ended up with, it would have to be 2 pivots, because remember, we always have to agree on what the dimension of something is. It can't be that I do some EROs and I end up saying that it's 2-dimensional, and then Caesar does the exact same matrix, does some different EROs, which is perfectly correct to do that. There would be no way that he could come up and say, oh, there's only 1 pivot, and so it's only 1 dimension, right? We have to agree on how many vectors are in the basis. There's a correct answer for that. But what the actual basis is, there's some room, there's some wiggle room there. Depends on what EROs you did. Okay, one more thing is the third state. Are we good? So far, so good. The null space, the row space, guys, this is super easy. You just take your matrix, you do EROs, and you write down the pivoted rows. That's your basis. The dimension is how many pivots you have. That's pretty much the whole story. It's not a whole lot else to say.
For that span, if you put it in a matrix, it's going to be a 3x4, and because it's stretched out, that's going to tell us that we're going to have a free variable, right?
Correct. If you actually wanted to test whether these vectors were Li, you'd lay them into the columns of a matrix, and it would be a 3x4 matrix. And already, because it's a wide stretched out matrix, there would be a free variable, which means you know that these vectors are LD. You know this can't be a basis. It's too many vectors. I mean, the universe of R3 is only 3-dimensional, and you've already got 4 vectors here. That's $4,000. That's too expensive. It's not going to be a basis. Yeah. Great point. Great point. Okay, I bet you know what the third subspace is going to be. Anybody want to try me? We just talked about the row space.
The column space.
The column space. Of course, it's going to be the column space. Yeah, number 3 is called it's actually usually abbreviated call space of A. The call space of A. So let's get that up here really quick. This is just, by definition again, going to kind of do the same approach. I'm just going to define it as I go along. The definition of the column space is it's just the span of the column vectors of A. And not to sound like a broken record, but because it is a span of something, it is a subspace. But what is it a subspace of, do you think? The columns, and we can have an example to remind us. If we look at this example, the columns have 4 slots each, right? And the 4 is coming from the M value. So this one's different. This one's different. The first 2 examples were subspaces of Rn, but this one is a subspace of Rm. Rm. So for our example here, it would be a subspace of R4. Okay. And again, let me just go back to the example above and just kind of write how that would look. For the example above, the call space of A would be the span of, and now I'm just going to write my columns. So the first column is 1, 2, 0, 1. I'm writing it as a vector. So that is a single column vector. The second one is 2, 1, 1, 0. And then the third one is 6, 6, 2, 2, like that. By the way, you might notice that when I was talking about the row space, I was writing everything as rows. And now here I am on the column space, I'm writing everything as columns. Technically, you don't have to adopt that convention. Like if I wanted to just be kind of a rebel, I could write this basis here like this, and I wouldn't really be wrong. Okay, it would be kind of a misleading way to represent these two vectors, but you don't technically have to write row vectors as rows or column vectors as columns. It doesn't really matter. But you're going to see me try to do that. I'm going to try to do that. When I'm talking about column space, I'm going to be writing things vertically. When I'm talking about row space, I'm going to be writing things horizontally. Okay. Now, what about, again, I could ask, what about finding a basis for the column space? I can guarantee you that these three vectors are a spanning set for the column space, because that's how the column space is actually created. It is created as the span of those vectors. So that almost by definition is making them a spanning set. The issue here would be, are these vectors Li or not? And this time it's not obvious. Over here, it was a clear no. 4 vectors in R3, no chance that those could be Li. K is too big. But here, the K value is only 3, and these are vectors living in the universe of R4. So that's kind of the maybe scenario. If you remember from the chart, they might be Li. So you would have to test that, except that it turns out that somebody else has already done all this work and figured out how to get your basis for your column space at A. So I'm going to give that to you here to get a basis for the call space of A. What you're going to do is you are going to, this is a little tricky. You might think that I would just take the pivoted columns, because this over here, to get the basis for the row space, I took the pivoted rows of the row echelon form. For the column space, we can take the columns of A that correspond to the pivots in the row echelon form of A. I'll let you write that down, and then I'm going to stop and explain what the heck I'm talking about. All that this means is that, okay, so when I was doing the row space, I just took these pivoted rows directly. I just wrote them down as my answer. When I'm doing the column space, I see where my pivoted columns are, which are these first 2 columns, but I don't write down the first 2 columns, guys. What it says is take the columns of A. So I actually have to take, oh, these are the first 2 columns. I'm going to go back to A and write down the corresponding columns from A. Why do you have to do that? Oh, it's because the EROs are row operations and they mess up the columns. So the column space of this matrix has been messed up from the column space of the original matrix. And so I actually have to, I'm forced in this case to go back to the original matrix. So in this example, the basis for the call space of A is, so the nice thing is I've already done the row echelon form. Notice I'm getting all 3 subspaces, 3 for the price of 1. I did 1 set of EROs, and I'm getting my null space, my row space, and my column space from it. I just have to go back to the original matrix. I'm going to take the first column right there, 1, 2, 0, 1, and then the second column is 2, 1, 1, 0. And the dimension of this since I talked about the dimension of the row space, you probably would like to know the dimension of the column space of A is also equal to, it's also equal to the number of pivots, which is the rank of A. Caesar.
Is this at all, like, I know how we're taking the first two original rows. like,
Columns, yeah.
columns. Before in another lesson, we reverse the ER. Is that something that's at all applicable here? Like, kind of like, oh, if you.
Let me think about that. That's possible that there's a connection there, but I'd have to think about that one a little bit. You're thinking a little bit deeper than I am right now about this. I am basically out of time, so I need to make two quick comments. The first one is that the homework that's due tomorrow, I am going to shorten this assignment. So after I go down to my office, I'm going to move some of these problems to a recommended section. I am also going to make a video solving a lot of these problems for you. 48 and 49, nobody ever knows how to do them because it's very theoretical and abstract in 4.5. But I want you to look at that. So I will solve them in the video, and I'll do some more of these as well. A lot of these are really quick, guys. A lot of these problems, they're just going to say, oh, is it a basis for V? And you're going to say, oh, K equals this and dim V equals that. Oh, no, it's not a basis. Some of the problems are just like that. So that's one thing. The other thing I wanted to point out, if we go to the file section in Canvas really quick, there is a special handouts folder. And in here, there is a file that's called recap of 4.6, 4.8, and 4.9. And down here on the bottom of this handout is a nice summary of everything we just did in the last 20 minutes, which is basically null space, row space, column space. What are those things as a description? What are they a subspace of? What are their dimensions? And how do you get a basis for it? Literally, the entire lecture is summarized right there. You don't even need anything else. And oh, and of course, our new favorite theorem of the semester, the rank nullity theorem, is here. That's certainly a good one to know as well. So keep in mind, that's in there. I would print that out and put it under your pillow every night for the next 2 weeks before our exam. And that way it'll soak into your mind as you sleep. Have a great rest of your Thursday, everybody. And I will talk to you all again soon. Thanks for being here. Yes.
How soon will you,
I'm going to edit that list of problems right when I get a chance to be alone for 5 minutes down. You're going to work on it right now. I'm going to go edit that within the next 10 minutes. I'll close my office door briefly to get back. Yeah, no worries.